Well, g'day flatties and globe defenders. It's Critical Think, normally from down under, but today I'm coming to you from my new studio in Thailand. Thank you. Now you can see I've got some new equipment here for this particular studio. I've got one of these spit shields and a very professional looking microphone there. But I don't know really how good it is, but we'll see what happens here. In the background there, I've got a picture of the Mekong River. Now, that's taken at Nong Khai, which is on northeastern part of Thailand, across the river from Laos. Now, the river level is very low, and some people are blaming that on upstream dams, and other people are saying, well, if they get some decent rainfall, the river level will rise. Well, I hope that's the case because the fishermen and locals there are suffering quite a bit because of the low water levels. Anyway, let's get to today's video. Now, here we go with another experiment of weight change versus latitude. You probably know that this is my favourite experiment, and it's empirical evidence that confirms we live on a rotating spheroid. So when somebody says no evidence of rotation, here it is. This is pretty solid evidence, as we'll see. Now, why is this experiment so fabulous? I mean, I love this experiment. And I've explained this before, but here we go again. The results are sort of unexpected. I mean, who would think that as you go towards the equator, you're going to weigh just a little bit less, and this little bit less is in fact measurable, and it's a non-optical observation, no refraction required. You know, there's a lot of flatties, they come and ask me, do you have a non-optical evidence of curvature? Oh, yes, we do. It's this experiment, non-optical, no geometric horizon required. Isn't that good news? And there is no flat earth explanation for this naturally observed phenomenon. It's observable, testable, repeatable, and falsifiable. And anyone can do the experiment. Even flat earthers could do it if they really tried, and I know one that has. Now, if there was no R, it would not work. So when flatties say you're going to need an R for that, well, if you didn't have R, this wouldn't work at all. So yes, we have an R for that. And if there was no rotation, it would not work as well. So not only do we have an R, we have rotation. Everything you need to disprove the flat and stationary Earth. Now, there are some sites on the internet that do discuss this. It's not very popular, not all that well known, but look at that. And even the manufacturer of scales are completely aware of this effect of gravity being different at different latitudes. So it's no big mystery to the people that actually manufacture the scales. Another thing that in the past it's been mentioned that, maybe the weight changes because of magnetism or density or whatever. Any excuse will do, just as long as it's not curvature, because we can't have curvature, can we? They can't have an R, can't have curvature. And so every evidence of R and curvature, etc., must be denied by those that must be flat. So I did do another video a little while ago about how magnetism has 2/5 of bugger all effect on weighing a 500-gram weight. So you can see it's not magnetism that makes the weight change. It's something else. Let's take another look at the equipment. The equipment is slightly different this time. Last time I compared two Digitechs. One was suspected to be broken, and then a new one, which is the Digitech on the right. Now, the broken one has been put aside, maybe able to use it for spare parts or something. And I've bought a brand new scale that looks very good, looks very promising. It's got a 0.01 resolution on the display, and it goes up to 2,000 grams. and I thought I'd give that a shot. If this scale was any good, I'd use it because it can go over 1,000 grams. This is important because as you move away from the equator, if you're weighing with 1,000-gram test weight, then your scale's not going to go overload. Like the Digitech on the right will go into overload if it exceeds 1,000. And that's a little bit of an issue with that one. But in this case, we're only going towards the equator, so we can weigh 1,000 and it will get less and less as we go towards the equator. So no problem this time. I also tested this particular El Cheapo scale. It's small, it's cheap, and if it works, people could use that to conduct the experiment and get some meaningful results, although not as accurate as using one of those precision scales in the previous slide. I've also got this neat weather station that gives me the air pressure, the temperature, and the relative humidity. And all of these things used for calculating air density. And for the first time, I've got the relative humidity reading there. I've also got the pressure reading and the magnetic field reading from the smartphone, as well as the GPS position and elevation. Now, the pressure reading was used as a check on the other weather station, and although they tracked identically, there was a small consistent difference between the two readings, but they did track relatively speaking. Now, the method is as before. Make sure the scales are level and weigh 500 grams on every scale, and weigh 1,000 grams on the scales that can cope with it. Take all the readings and record them. Now, the measurements. The measurements were taken on a road trip up to North Queensland. During recent times, we were more or less only allowed to travel within the state because of border closures, etc., etc. So this was a good trip to do. It's quite a long way from 27 degrees south to 16 degrees south. I started out here at Redcliffe and then went up the coast, took measurements at Childers, Rockhampton, Mackay, and Castle Hill and Townsville. Then went to Atherton, through Atherton to Cooktown. Now, at Cooktown, we stayed about a day or so and then went back to Cairns, took another measurement, and stayed a couple of days in Cairns, and then came down through Charters Towers. There, first time I've been in Charters Towers, and Emerald, and Roma, and then back to Redcliffe. So let's have a look at the results. Here's my spreadsheet that I use to analyze the results. It all looks a little bit busy there, but basically if you look at that graph up to the top right there, that jagged line at the top is my attempt at plotting the effects of relative density, which a lot of flat earthers are a fan of. But as you can see from the graph there, the measurements do not track anything to do with relative density. And I've got the WGS 84 prediction there in the lower blue line, and the orange line is the measurements on my Digitech scale. And look at that. Look how close that measurement is to the predicted value from a rotating spheroid. That's almost spot on. In fact, you couldn't do much better than that in any measurement with this type of equipment. I mean, that's just absolutely fabulous. And of course, it's going to shoot a whole lot of holes into the flat earth argument. Yes, indeed. Now, I'll just show another couple of things from this graph. We'll show the other scale, which was scale 1, and we'll take the flat earth off there. We'll just show the other scale. As you can see, it still follows the prediction, but it has a little kink here and there. So it's pretty good, but not as good as the Digitech. And let's have a look also at the 500 gram weight. So we'll select those. Okay, so that's again scale 1 is got a few deviations that are different, and scale 3 has got not as accurate, but it would be okay if you did this measurement with an El Cheapo scale over a wide range of latitude. You would get a meaningful result, but some of the points would be a little bit off, as shown here. Now for this graph, I've normalized all the measurements with a calibration of 1,000 grams at 27 latitude and an elevation of about 19 meters. Then I've plotted all the points in relation to the WGS 84 prediction, which is the green line. And as you can see, the dots are all scattered all across and all follow that green line. Now for comparison, I've added the purple line, which is the rotating sphere, and the brown line, which is the stationary spheroid. As you can see, both of those things by themselves don't explain the measurements, but if you add those two together, that is a rotating oblate spheroid, then you'll get all the measurements there that line up with that. So that's amazing confirmation that the WGS model is pretty good. It has great predictive powers. So that's why we can be fairly confident that this model is an accurate representation of our reality, because we can go out in reality, take some measurements of weight, and it matches the model. So that gives confidence in the model. Now I've combined all the measurements that various people have done as well as my own runs. I've even plotted on this plot now my latest measurements from Thailand and Sydney, and they all cluster around the WGS 84 line. Now, if there was no effect of weight changing versus latitude, then all the dots would be clustered around that blue line there. But things change, and as predicted, it follows the WGS 84 model. Now, that's pretty good there, except for that 1 point, Bob. What happened here, Bob? Oh, never mind. I think we could really eliminate that one because that one looks like the odd man out. But it's there. We've included it in the data. It's swamped, of course, by all the other measurements. But every now and then something untoward may happen and you get a crazy reading. Now, from my collection of data, those 13 points I took in September 2021, I've got it that the WGS model explains 98.6% of the variation. Now, this was using the coefficient of determination calculations, which I've explained in a previous video. Now, the sigma for this particular run, which is the standard deviation, is 0.02, which is amazingly good. Now, the scales themselves, even though they have a 0.01 resolution, they're only accurate. They're only guaranteed to be accurate to 0.1. But in my experience, the scales do vary by about 0.03, and this sort of backs that up. Now, when I take the totals of 74 points, I still get the WGS 84 model still explains 98.5% of the variation. Now, that is a very, 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 very good fit. And then with all those readings, a little bit more variance of 0.088. Now, what does all this data mean, and why is it such a crushing blow to the flat Earth? Well, you know, people in the flat Earth, they say, oh, but the weight could be changing because of, insert something there that's unproven, anything you like. But if that were really true, then this is the plot that you would get. If the weight were to vary by the same amount as we observed, and due to some non-correlated effect. It could be temperature, magnetism, density, anything you like to pick, anything in the world, flatties. Although you've never established such a relationship that exists, then these dots would be all over the place in relation to the WGS84 because there would be no correlation. And so you'd get a plot like that. But we don't get that plot, do we, flatties? No, indeed, no. So here's something else. The null hypothesis there, the blue line there, this is the kind of variation we get. We've got these green dots up the top clustering around the blue line. Now, this makes a lot of sense because we're using precision scales. You don't expect the scales to read 1 gram difference when you've actually got a 0.01 accuracy scale. So there will be a little bit of error, a little bit of variation. And in practice, these dots, these green dots here, represent the magnitude of error that we would get with the scales. Now, then you've got to look at this in terms of standard deviation. If these blue dots were random events, then look how far away they are from the null hypothesis. So you've got the standard deviation on these 13 points of 0.02784. And the null hypothesis says these points should always be up near this blue line. But look at how many points we've got that is so far away. I've got 9 sigma there, 20 sigma there. I mean, it's just astronomical, the odds of these things being random events. This, 5 sigma is thought to be really good for nuclear physics. But these points, they're way outside that. So I'm not going to even attempt to try to calculate the gazillion to 1 chance that this would be an accident. So there you go, flatties. There's no accident that these dots follow the rotating spheroid model. The rotating spheroid model predicts that if you take a measurement of weight at various latitudes and elevation, it will follow this line. And that's the evidence for curvature, for R, for a rotating spheroid. What do you got? What do you got to counter that, flatties? What do you got? Got any measurements? What are you going to do now? Now, I always play this clip on these weight change versus latitude videos. Some will say, oh, but that was years ago. Yes, it was years ago, but it's never been retracted, never been corrected. And so because it's never been retracted and corrected, it's still wrong. It's still wrong. Until someone admits that they were mistaken, maybe another flatty would have the courage to tell Phuket Word that he was mistaken. But anyway, here we go.
Goes on about the difference in the weight of things at the equator compared to other places in the Earth. Have you actually gone and measured it? Have you ever done it? We understand that in the model, based on the spin and centrifugals, centripetal, whatever forces, that's the result that you can calculate based on your model.
And we did.
But has anyone actually gone and measured this so-called difference? Has anyone actually measured that a kilogram weighed in the, somewhere up north is any different to a kilogram weighed on the equator?
Yeah.
Has anyone actually gone and done that? No, they have not. A kilogram is a kilogram wherever you are on the Earth.
Never gets old. So that's it for today. So please like and subscribe. If any flatty ever asks about where's your evidence of curvature or measurement of R or things like that. This is one of those things. There's quite a few things, but this is my favourite, mainly because no optical measurements are required.